Welcome to this session. My name is Mario BALDI. I'm a fellow at Pensando Systems, and I'm going to present a fully programmable system on chip for the network edge. Let me first of all set the context of why we need a fully programmable system on chip at the network edge. Data centers today require to run a number of services. Network services like, for example, network address translation, load balancing, creating overlays, for example, based on VXLAN, security services like firewalls, intrusion detection systems, intrusion prevention systems, storage services like shared disks, disaggregated storage, and observability services, being able to collect telemetry information, being able to capture packets. So where do we run, where do we implement these services? Traditionally, these services were implemented in appliances, which could have been virtual appliances, so software appliances running somewhere in the network, and where they could have been embedded in switches, they could have been executed in hosts, and this is the case of network function virtualization. But having an appliance where those services are offered has implications on the way we design the topology of our network and the way we route and stitch traffic so that it goes through the appliance that's offering services. And this model of having a centralized appliance that's offering a service works well for a certain type of traffic, like the north-north, what the so-called north-south traffic, the traffic that's going towards the internet or is coming towards the internet into the data center, because this traffic naturally goes through a single point of entrance or exit of the data center network, which is the point in which the data center is connected to the internet through one or a few routers. And so here traffic has to go through this area of the network, and that's where we can install our appliance. However, in data centers today, we have also a lot of east-west traffic, so-called east-west traffic, which is traffic that is exchanged between hosts or servers, we could say, within the data center. According to some estimates, this traffic is over 90% of the traffic of the data center. And this kind of traffic doesn't fit well to the solution based on an appliance, because we would need to route that traffic through the appliance so that the appliance can offer the service that we want to have in the data center. And this has implication in how we route the traffic, and we create what is called traffic tromboning. We have traffic that goes between two servers that are topologically quite close, and we need to have it go through the whole data center network to the appliance and back with this shape that reminds a little bit the shape of a trombone. And this creates additional traffic on parts of the network that otherwise would not be affected by the traffic, and it has implication on how we do routing. Instead, if we could distribute services through the network so that the traffic naturally following the route, the shortest route or the optimal route from the source to the destination, hits the service and gets processed according to that service, we would not need to change the routing. We would not need to load part of the networks that would not be loaded. And also, we would not need to add additional latency to our traffic. So where can services be implemented in a way that they are found naturally by the traffic in the network? Well, one option is to implement those services in network nodes. And the idea of implementing services in network nodes has been around for a long time. For example, years ago, we were talking about active networks where packets would contain instructions on what devices had to do on them. And that's just one flavor of implemented additional services in network nodes, or we could implement those services in end systems. So let's take a look at the challenges that we have in either of those cases. Now, if we want to implement services in network nodes, we have to deal with the fact that network nodes handle very large volumes of traffic, which means that they have very short time to process packets. And this might not be suitable to implementing complex services. Moreover, network nodes have been designed for forwarding packets, so for implementing relatively simple tasks, and they are often based on fixed function devices, fixed function ASICs, application-specific integrated circuits, that in fact execute simple functions and cannot be changed. For a few years we have been talking about P4-based switches that are programmable using the P4 language. And so this could provide an opportunity for implementing more sophisticated services, newer services that were not originally offered by network nodes, and have those services executed with the same performance of hardware, of fixed function hardware. However, again, we have a challenge in network nodes because they deal with large amount of traffic. So one possibility could be to say, okay, let's implement those services in the hosts at the edges of the network. Now, if we implement those services in hosts, usually we do it using agents, but those agents consume the CPU of the host, which should be used for offering whatever services those hosts are there to offer, application level services, not the kind of infrastructure services we are talking about here. This is one disadvantage of executing security, networking, storage, and observability services in hosts. Another issue is that usually we implement those services with agents, and hosts are running different operating systems, so we would need to support various operating systems with those agents. And this is problematic. It's also problematic to handle the various updates of the operating system. When an operating system gets updated, we need to make sure that we have a version of the agent that's suitable for that particular version of the operating system. Very complex to manage. But not only, but then we have a number of challenges that are common to both hosts, to both services implemented in hosts and services implemented in the network. First of all, we need to configure and control those services. We need to be able to manage those services. And if services are distributed, when we want to change the configuration, we go and have to go and change the configuration in all of those different devices that are implementing the service. And we might have performance issues because if the device in which the service is implemented, being it a host or a network node, is not fully dedicated to the service, it's also dedicated to processing forwarding packets, or is dedicated to executing applications, then we might not get the performance that we would like to have, or the performance might not be consistent because when the node, the network node or the host has more load for other reasons, the service implementation slows down. How can these challenges be addressed? Pensando has developed a distributed services platform to implement services in data centers at the network edge. So at the edge between the network and the host, addressing the challenges that we have just described. This platform is centered around a component, a card that is installed in hosts, and it's called Distributed Services Card, or DSC. And this card includes a programmable processor that contains both ARM cores and application-specific processors organized in a pipeline. And we'll get back later to why is this card programmable and why do we have these kind of processors. But let's first of all see what's the idea behind this platform and how it addresses the challenges that we have discussed before. So this card is installed in every single host, and that's where services are implemented. So they are not implemented in network devices, and they're not implemented in the host itself using the host CPU, but they run on this card. So without loading the host CPU, without the dependency on the operating system running on the host. And then we have a centralized management point, which we call PSM, or Policy and Services Manager, from which we can configure and control those services. And we do this with a policy-based paradigm. The PSM offers a REST API for automation and for integration with other components, for example, with orchestrators, and it offers a collection point for observability data. So this solution, on the one hand, leverages the scale-out model typical of the cloud. The more servers you install in the data center, the more scalability you have, and this platform maintains that model because the more server we have, the more cards we have, but at the same time we have a single point of management, so the same management simplicity that we have with centralized appliances. So now, why do we need this card to be programmable? And this card is a data processing unit, is what we call today a DPU. It sits on the host and it processes traffic in and out of the host. Well, we want it to be programmable because the modern data centers, being them cloud data centers or enterprise data centers, are a very dynamic environment. We have continuously changing requirements, which also come from the fact that most often in data center, the applications are deployed and developed using a continuous CD/CI, continuous development, continuous integration model. And moreover, these services that we want to implement are new services, so they are still evolving. They are not stable like the traditional layer 2, layer 3, layer 4 network services. Some of these services are complex, and so they require general purpose processing. We cannot address them with ASICs, with fixed function ASICs. And also, many customers have specific requirements. First of all, some large customers like cloud providers, they want to own the solutions they use. They want to be able to add features, change the features the way they want by themselves. We have different customers that want different features and functionalities. And finally, there are some use cases that are very important, but they are important for a very limited market. So it is not justified for the vendor of the solution to address those. So if we have a customizable solution, a programmable a solution based on a programmable device, the end customer, the end user, can customize it the way they want. Now, why do we use ARM processors? We use ARM processors because we need general purpose processing on the DPUs that are being deployed at the network edge. And, you know, I am using the Pensando Distributed Services platform as an example, but many of the statements I'm making, many of the aspects I discuss apply also to DPU of other providers. We have a requirement to have fairly complex processing. We want to run control functions and management functions on those DPUs. So we need general purpose processing. For example, ARM. And why ARM in particular? Because ARM offers a low footprint, low power consumption, and low cost. So really good for this kind of device. And in fact, many of the data processing units, DPUs that you find today on the market, contain ARM cores in different shapes and in different combinations with other components, or possibly without other components. And you know, one aspect that in my opinion is really key is that there have to be different processing components. And what is key is using them together to get the best from each one of them. So they have to be tightly integrated. This way we can provide the perfect support for any service in terms of providing the necessary functionalities, providing the performance and the efficiency in using resources. And because we have other components, we can use ARM cores really for what they are best, and consequently use them as efficiently as possible. Now, what does the DSC architecture look like? First of all, we have a PCIe interface to connect the card to the host. Then we have two Ethernet ports that provide network connectivity. And the Ethernet ports are attached to a packet buffer, which includes also traffic manager, where we can store packets as they are received and as they are being processed. And they can be processed by packet processing pipelines that are programmable through P4. And packets can go from the packet buffer through those pipelines being processed and then being either sent back to the packet buffer and go out of the Ethernet interfaces, or go through the PCIe interface to the host and vice versa. Or for some of the packets, we can use ARM cores. In our current chips, we use A72 ARM cores. And finally, we have a number of service processing offloads, which are fixed function ASICs that we can use for functionalities that are particular resource intensive. And finally, we have a large amount of memory, from 8 GB to 64 GB of memory to store data and to store packets that we might want to store in the for a longer time in memory, and so we move them from the packet buffer to the memory. Now, that was the hardware architecture. What does the software architecture look like in such a device? Well, the idea is that we want to do any protocol processing in the P4 programmable pipelines, because those are specifically designed to efficiently process packets. And any exception from the normal processing, or any processing that requires more sophisticated operations, can be done in the ARM cores. And the business logic can be implemented in the ARM cores if we want maximum flexibility for complex logic that we want to implement, or it can be implemented in the P4 programmable pipelines to have higher performance, maximum performance. Now let's take a look at a couple of sample use cases to see how these various components in the architecture, in the hardware architecture, can be used when we implement specific services, specific functionalities. Let's take as an example TLS offload, transport layer security offload. And this is a typical offload in a SmartNIC, right? We want to offload in a SmartNIC protocol processing that is particularly resource intensive. And although the DSC, the distributed service card, is not just a SmartNIC, it can be used as such because it is connected to the PCIe bus and it has Ethernet interfaces. So which functionalities we want to mostly offload are the ones that require more resources in terms of memory and CPU. And TLS is a good example because it requires to manage TCP connections, which is memory intensive, maintain TCP state, the state of the TCP connection, and performs the management of the TLS sessions, which also is sophisticated. And finally, TLS requires data to be encrypted and decrypted, which is computationally intensive. So it's a good example of protocol processing that we may want to offload to relieve the CPU from this. How can we do the offload? One way is to implement a proxy in the DPU, or in our case, in the DSC itself, where applications use regular TCP to port 80, for example, and then the proxy receives connections to port 80 and translates them into secured, so TLS connections to port 443. And again, port 80 and port 443 are just an example. The idea is the applications do not encrypt traffic, and then the encryption is performed within the distributed service card. So where are the functionalities typical of TLS offloading, of this proxy I was talking about, being implemented? Well, packets are generally processed by the pipelines, by the P4 programmable pipelines, because we want maximum performance when we process packets. But whenever a message is starting a new TCP connection or is part of a TLS session negotiation, it is punted to the ARM cores, where the connection, the TCP connection and the TLS session initiation are processed. And once the required processing is concluded, a flow is installed in the P4 processing pipeline, so that the following packets are going to be processed only in the pipeline, and again obtain maximum performance. Packets are processed in the pipeline, but since they need to be encrypted and decrypted, encryption and decryption is performed in a service processing offload that has higher performance and is specialized to perform encryption and decryption. So here we can see how the ARM cores are key in handling those operations that are more sophisticated, like the connection, TCP connection and TLS session setup and tear down. At the same time, though, regular packets that need to be processed just according to TCP are processed within the P4 programmable pipelines to ensure wire speed throughput, minimum delay, and minimum jitter. Now let's look at another use case, which is the one of an east-west firewall. Now, east-west firewalling is particularly challenging, first of all because east-west traffic in data center, as we said, is much larger compared to north-south traffic towards the internet. Moreover, applications that are communicating within the data center expect much smaller latency than applications that communicate with the internet. So the firewall is supposed to introduce a very small latency. And finally, appliances are not suitable for handling east-west traffic, as we were saying at the beginning, because they generate traffic, they cause traffic tromboning. So the perfect spot where to implement an east-west firewall is within the DSC, because it is naturally on the path of every packet that is moving within the data center. Now, the way we implement east-west firewalling in the DSC is by using a flow cache so that we can reduce latency. So the idea is only the first few packets will be evaluated against a rule, and then once the rule against a set of rules, and then once the rule that the particular flow matches is identified, a flow entry is created in a flow table and associated with the action that the rule identified for that particular flow. So let's take a look at the architecture of the DSC and see how the firewall is implemented on such an architecture. So as usual, packets are being forwarded normally through the packet processing pipelines in order to achieve higher performance. And that's where, first of all, we check if a packet matches any of the entries in the flow cache. If so, then the packet is handled according to that entry. So, for example, forwarded or dropped or whatever else. Otherwise, if the packet is part of a new flow that's not already in the flow entry, the pipeline, within the pipeline, the packet is processed, is matched against the rules, and the matching rule is identified, and at that point the packet and the corresponding action that the rule contains are passed to the ARM core. The ARM core is going to create a new entry in the flow cache for both the forward and reverse direction of the traffic, and then the packet is injected back into the packet processing pipeline for being processed at this point according to this new entry that has been created, and following packets are going to be processed according to the entry. Notice this, because of the tight integration between the ARM core and the processing pipeline that are sharing the same memory, once the flow table is updated by the ARM core, immediately it is updated also within the packet processing pipeline. Now, we have seen a few use cases, how they can be addressed, but another very important aspect is how can we make such an architecture programmable? Because as we said, there are customers who will want their own features, customers will want to address specific use cases. So if we look at the architecture now from a higher perspective, and only if we look at the programmable components, we have ARM cores and we have pipelines of domain-specific processors. So the ARM cores are running an operating system and a number of processes that we call infrastructure processes. They monitor and manage the card to make sure that it operates correctly. In addition to that, on the ARM cores, we have all the control and management functionalities like routing protocols, and packets, as we said, are normally processed in the pipelines, unless there are exceptions for which they are processed by software running on the ARM cores. Now, a customer that uses these cards might want to customize each one of these layers of software. So we have a number of options for customizing or even just integrating the card in an existing environment. So the card offers an API that can be used to leverage software that is being pre-installed on the card, or a customer might want to just run an agent on the card for management purposes, or for example, for providing an API translation to use a different API than the one we offer. Or another customer might want to completely customize both the control plane, management plane, and the exception data path while using the fast data path that is provided on the pipelines, P4 programmable pipelines. Or a customer might want to also customize those pipelines, or finally, they might not even want to use the infrastructure and operating system provided with the card and develop their own. So we want to be able to support all these models. What I'm going to do in the rest of this presentation, I'm going to go through the various tools that we offer to support these various models of customization. So we said the first option for a customer is to run an agent on the ARM cores. So we allow users to run their applications in a container. We call those applications Pensando apps, but they are developed by customer and they run in an isolated environment. Now, these applications are not going to be on the data path, and so they will not see packets coming in and out, but they will be able to, be usable for management purposes, or for example, for data consolidation. They could collect logs and then create summaries on the card itself so that those logs don't need to be exported. They could generate alert from data that they collect directly on the card, or they could be used to translate the API. So for example, like shown in this drawing here, a customer could use their own homegrown controller rather than using the Pensando one, and their own API to communicate with the card. An agent running on the card will translate the API, the proprietary or anyway different API of the customer, into the native API of the card. Now, To run these applications, we have developed a lightweight container schedule called Penvisor that is leveraging the Linux namespaces for CPU and memory isolation, but it doesn't provide virtualized networking. So all the applications running in those containers share the same network interfaces. And again, the customer can use any development environment they want to develop these applications. They just have to compile them for 64-bit architecture, and they can be uploaded to the card and run onto the card. Now, another model is where customers want to develop their own exception data path and possibly their own control plane and their own management plane. So in this case, customers will leverage the operating system and the infrastructure that Pensando has developed for the card, but they will install and run their own logic for the control plane and the exception data plane, and possibly even for the fast data plane, in which case they will have to develop P4 code. What kind of application can we support with this model? Well, we can support applications that have custom processing logic of packets, like, for example, specific filtering of packets, specific access control, or specific routing policies when packets are routed, when packets are forwarded, or custom protocol processing, like custom tunneling solutions, proprietary protocols, or protocols that are not extremely common, or custom control logic, like different routing protocols, different path computation algorithms, different ways of discovering endpoints or terminating tunnels. Let's now see what are the tools that we make available for developers who want to write their software to run on the ARM cores on the DSC. So first of all, we provide a set of libraries that can be used, for example, to receive exception packets that are punted to the ARM core from the before programmable pipelines, and this is based on the PDK. Similarly, the PDK is used by the software running on the ARM core to inject packets into the packet processing pipeline, either to be sent out through the Ethernet interfaces or to be sent to the host after having been processed in the fast data path. And finally, since the packet processing pipeline is programmable through P4, and P4 allows to define tables, we have a set of libraries which we call the table level API that allows the software running on the ARM core to write, modify, and delete entries in the tables that have been defined in the packet processing pipelines. And finally, we offer a pipeline emulator and a testing environment that can run on an x86 processor, so that developers can write actually their software on an x86 platform, test it on that platform using whatever development tools they want to use for writing their software, and then they can use the tools that we offer to build an image to be uploaded on the card and used on the card. So to conclude, we have seen that there are significant benefits in distributing services at the edge of the network, so at the separation point between the network and the host, specifically in a data processing unit. And we have seen that programmability is a must in such a device. Actually, not only the device has to be programmable, but it's important that it contains multiple types of processing elements. In the case of the Pensando Distributed Services card, we have seen that we have general purpose processing elements, which are ARM cores, domain-specific processors organized in pipelines, and offloads, hardware offloads for particularly computationally intensive computations like, for example, compression, decompression, encryption. And having these kind of different processors well integrated is important to provide ideal support for any service that we want to implement on those cards at the network edge. And moreover, it's important to offer also various options for custom developers, for those users of the DPUs that want to develop their own solutions. And having these kind of architectures with programmability and various types of processing elements enable offering high performance, but at the same time enabling customizations on the card. Thank you for staying with me all the way to the end of this presentation. If you have any questions, you can contact me at the email address on this slide. And if you are interested in the innovative and exciting technologies we are working on at Pensando, you can find a lot of information on our website referenced here, and interesting articles on our blog at the URL on this slide. Thank you.